Here we're solving for an electric field for an infinite line of charge. Check that, a finite line of charge at a distance x. Total charge Q and length 2a. A small piece of the electric field will be proportional to 1 over 4 pi epsilon naught, and also dq over r squared. That's the main piece we're working off of. In this demonstration, you'll see how dq is found, how r is found, and how to determine the components of the electric field. So we find our distance to the little piece of charge right here, dq. This is a piece of the overall charge q, and it has a little tiny length or a little tiny size we'll later define. And we'll say the distance horizontally from this midpoint of the charged rod is y. So that makes the distance between the point where we're looking for the electric field and that little piece of charge dq square root of x squared plus y squared. All right, so this is what we can define as r. That'll go in here. R is the distance between dq and the point we're looking for, the electric field. All right, so how much is that little piece dq? That's what we're looking for right now. We can compare the total charge of the rod to the total length of the rod. And that ratio will be the same as the little piece of charge dq to the little piece of length. Now the length right in here is on this little y-axis, or large y-axis, and it'll have a little dimension dy. So here we see that dq is equal to q over 2a dy. All right, so now we put it together, and we find dE is 1 over 4 pi epsilon naught q over 2a. So I'm going to substitute and write it here, and that leaves us another dy in the denominator, or the numerator, and r squared would be the square root of x squared plus y squared quantity squared, which just leaves us with x squared plus y squared. Now that's the magnitude of E, but what we'll find is that if this is a positively charged rod, then there will be an electric field going out this way due to that little piece dq. There's also a little piece dq over here, which we're going to finally add up in the end, which would have an electric field in that direction. The magnitudes of electric fields at this point would be the same for these two little pieces dq, but their opposing vertical components would cancel each other out. So by symmetry, we can see that dE in the y direction, if we sum it all up, should equal 0 because those components do cancel. All right. However, in the x direction, coming out this way, these components in the x direction don't cancel. They're all directed outwards. So we end up with an expression dE for the x direction equal to 1 over 4 pi epsilon naught, just copying this down, q over 2a dy over x squared plus y squared. And the x direction component with the cosine of an angle that I'm going to define right here. Cosine is the adjacent over the hypotenuse, so I'm looking at this component as opposed to the y component of a right triangle. And this angle would be the same as this little angle down here, which any way you look at it is the cosine component. So the last thing we should define here is the cosine of theta in terms of x and y is equal to x, the adjacent side, divided by the hypotenuse, square root of x squared plus y squared. So this whole expression we get down to set up for an expression that we can later integrate So if we substitute this expression for cosine, then we end up with an x dy over, now there's this quantity x squared plus y squared, and also multiplying it by the denominator over here. This is x squared plus y squared to the 1/2 power. 1/2 times 2/2. Exponential powers means we add the exponents, gives us an x squared plus y squared to the 3/2 power. And this is an expression that's can be integrated. We're just going to sum up all the electric field in the x direction. Now the bounds for this expression will be from a negative a to a positive a. And that would incorporate the entire length 2a. And we're doing that because that defines our the position of E as a little origin position right over here. And that's the setup.